Hi, I'm Zenith Reyes, a biomedical science master's degree student in Juárez Autonomous University of Tabasco, Mexico. My project looks at what is the metabolic effect of cassava and sweet potato pyrodextrin at a different dose on a high sucrose rat model. Pyrodextrinization is one of the modifications that is made to native starches and confers to it to have more fractions of resistant starch through chemical reactions, such as this works by Toraya Vilés et al. And Lovera et al., showing a decrease in the available starch portion of cassava and yam pyrodextrins. Resistant starch is fermented by microbiota, increasing the production of short-chain fatty acids, which can act by triggering a series of physiological mechanisms regulated by the hypothalamus involving appetite and satiety neurotransmitters. Our team has performed metabolic evaluations such as Olvera Hernandez et al. On a high sucrose rat model. It was found that those groups which had treatments of native banana resistant starch resulted in beneficial changes in glucose homeostasis and levels in serum lipids. In addition, Friedhaus et al. Found that fasting glucose and postprandial glucose lowered with a cassava-resistant starch and modified cassava flour treatments. Moreover, both treatments increased plasma GLP-1 levels on type 2 diabetes mellitus rats. Our work consisted first with the modification of tubers' native starch by pyrodextrinization. Then, the evaluation of metabolic effect was divided in high sucrose diet induction and a treatment period, in which 48 Wistar rats were divided in 6 groups and a negative control. After 20 weeks, glycemia of positive control was 96.50 with standard error of 3.75 milligrams per deciliter, and negative control was 71 with standard error of 3.07 milligrams per deciliter. After treatments, glycemia of sweet potato pyrodextrin 1 and 2 were lower than positive control with 65.86 with standard error of 2.91 milligrams per deciliter and 69 with standard error of 2.84 milligrams per deciliter accordingly. Even though in serum triglycerides, sweet potato pyrodextrin 2 were similar to positive control, with 155.5 with standard error of 10.74 milligrams per deciliter. The treatment closest to the negative control was cassava pyrodextrin 2 with 107.71 with a standard error of 24.16 milligrams per deciliter. However, it didn't show significant difference with positive control. Serum cholesterol doesn't show significant differences between groups, although cassava pyrodextrin 1 was the lower value with 58.21 with standard error of 6.34 milligrams per deciliter, with 87.21 with standard error of 10.86 milligrams per deciliter of negative control. Finally, sweet potato pyrodextrin 1 showed 47 with standard error of 29.01 milligrams per deciliter of HDL cholesterol, highest than positive control, but not with a significant difference. So, in this case, sweet potato pyrodextrins presented an ability of decreased glycemia and increased HDL cholesterol. It may be due to its 47.15% of resistant starch, and cassava pyrodextrins may be able to decrease serum triglycerides and cholesterol, although cassava pyrodextrin had 24.42% of resistant starch. It will be necessary to study the serum GLP-1 content of each group to know the real mechanisms of both pyrodextrins. Finally, I want to remark this work was approved by Institutional Research Ethics Committee. Again, I'm Zenith Reyes and I'm a CONACYT Fellow. Thank you.